Hello, my name is Yixuan Wang from Shanghai, China. I am currently studying applied mathematics at Xi'an Jiaotong-Liverpool University. In aviation, safety is built on precision, and at the very core of that safety lies the jet engine. These engines, like the GE9X on the Boeing 777X, are incredibly complex machines, built with thousands of moving parts. A single fan blade failure or a bearing malfunction can cost millions of dollars to repair, and in rare cases, even risk lives. What if AI could identify subtle warning signs and predict failures before they occur? So today we'll explore how predictive maintenance using mathematics, AI, and machine learning is transforming aviation safety. We'll split this video into 3 parts. In part 1, we'll discuss why predictive maintenance matters. And part 2, we'll be looking at a relatively traditional but widely used methods of checking engine failures from a mathematical perspective. And in the third part, we'll be focusing on the newest technology with AI models added. Today, airlines still rely on 2 main actions to check engines. First, with regular inspections, what engineers call line maintenance before each flight and base maintenance during scheduled overhauls. Second, with alarms in the cockpit. But obviously, sensors trigger warnings only after abnormal behavior exceeds safe limits, similar to a fire alarm ringing after smoke fills the house. Yet despite all of this, sudden failures can still happen. Even when no lives are lost, such failures create massive ripple effects: emergency landings, diverted and grounded flights, and repair costs, often amounting to millions of dollars in losses. Predictive maintenance flips this. Artificial intelligence watches subtle patterns in real time, estimating remaining useful life for components, using data to schedule maintenance not by a calendar, but by the engine's real-time condition. So now let's look at signal analysis, which serves as a traditional way of checking engine failure. Modern jet engines now carry hundreds of sensors. They track temperature, oil pressure, vibrations, and rotor speed. So the technique often used in the past is to analyze different signals and manually determine the abnormal patterns. To make the showing process simpler, we only take one parameter, say, vibration. Vibrations to the human ear is just noise. That's where math, specifically Fourier transform, steps in. It may seem very daunting, but we can forget about the formula and just think of Fourier transform as a master sound engineer. Imagine walking into a crowded room where everyone's talking at once. It's overwhelming. But with the right tool, you can isolate individual voices, like pick out the tenor from the bass. That's exactly what Fourier transform does for engine vibrations. Here's how it works in the real world. Sensors on the engine capture raw vibration data. Fourier transform takes that chaos and decomposes it into a spectrum of frequencies, like separating a symphony into its individual instruments. On the spectrum, a healthy engine shows just a few clean peaks, but when something's wrong, new spikes appear. While Fourier transform helps analyze engine vibrations, it still requires manual interpretation by engineers. Today, AI models are expected to automate this process with greater speed and accuracy. To put it simply, we train AI models to listen to the heartbeat of a jet engine. A neural network is like a mechanic who has seen thousands of engines before. It learns the normal patterns of temperature, pressure, and vibrations, so it can quickly tell when something doesn't look right. But engines don't just have one snapshot of data. They produce a stream of signals over time. That's where LSTMs, or long short-term memory networks, come in. You can think of an LSTM as a mechanic with a very good memory. It doesn't just look at the latest vibration, but remembers how that vibration has been changing over the past minutes or hours. Together, these models help engineers spot early signs of failure, sometimes long before they become serious problems. These ideas are not just theoretical. NASA has already released an open dataset called CMAPS, which simulates jet engine degradation over time, and has allowed researchers globally to train and validate AI models for engine health prediction. Predictive maintenance as a term isn't new. In real-world operations, manufacturers and airlines are already adopting these technologies. Rolls-Royce's intelligent engine creates digital twins of engines to monitor and predict part wear in real time. Airlines and MRO providers are also on board. Lufthansa Technik's Aviator platform launched its first AI-based tool in early 2025. It automatically scans maintenance logs for repeating issues, cutting out tedious manual work. While the black box tells us what happened, predictive maintenance tells us what might happen. Next time you fly, remember, every hum and vibration is being analyzed. Mathematics, AI, and human expertise are working together to keep our flights safe. In aviation, the future isn't just reactive, it's predictive.